Welcome to video 2 on our road to the RSA encryption algorithm. Today we're going to talk about Bezout's lemma, and it's a lemma that allows us to work toward the following type of question. Say you have a line like this, and you ask not for what points are on the actual line, which we could get by graphing or finding a parametric equation for these, but finding the integer pairs x, y that actually satisfy this. As the numbers and the coefficients and the numbers on the right-hand side vary, questions arise like, when are there no solutions? When can we find a solution? If we find a solution, what's the full set of solutions? We'll be able to answer that question in a couple of videos from now. But what we'll start with is recognizing that if this number here, let's say, was replaced with a 1, which is the greatest common divisor of these two things, then we can find a value of x and a value of y that satisfy this equation. And it's going to follow from our first video on the Euclidean algorithm that's right over here. And along the way, we're going to see some interesting properties of divisibility and a characterization of the greatest common divisor that has nothing to do with prime numbers or prime factorization. So stay tuned to this video, the second video in our series on this interesting exposition of Bezout's lemma. Hey, welcome to today's video. I'm Prof. Omar. This channel is dedicated to theorems leading all the way up to the end of the undergraduate math curriculum for your journey through that whole entire process and for the journey beyond. If you're new to this channel, definitely subscribe to the channel, and if you're already a subscriber, thanks for coming back. This video is our second video in a series leading to the RSA encryption algorithm. We're going to build all the mathematics needed to get there. And today is going to focus on what's called Bezout's lemma. And to motivate the background of what we're going to do today and in the next couple of videos, I'm going to look at these three linear equations in two variables right here and ask the question, is there an integer pair xy that satisfy these equations? Let's play sort of heuristically first to get a sense and a feel of what kind of answers we could get, and then see what governs the process. So here, for example, if x was an integer and y was an integer, then you probably notice we get a problem because this left-hand side is a multiple of 8. It's divisible by 8, but then here we have a 1, which is not divisible by 8. So there's no solution in this case. Now here, you might think, well, if I plugged in x equals 4 and y equals 0, I get a solution. Or x equals 0 and y equals 3, I get a solution. But what are other solutions? Well, one way we could think about getting a solution instead is to start maybe with a solution to the equation 3x plus 4y equals 1. That has a solution negative 1, 1. And now, if we want to generate a solution for when this is equal to 12, we can multiply all the entries by 12 and get a solution that way. So this is a more complicated solution than setting 1 to 0 and the other one to a number that works. But it's at least a systematic way to start with a smaller number and build up to a bigger one. That kind of technique is going to be useful for us in the future. Okay, here we could do sort of a similar thing where it may not be clear how to make a linear combination that gives you, or an integer combination that gives you 9, but we can make a 3 by setting this to negative 1 and setting y to 1. And then because of that, we can multiply throughout by 3 to get a solution for when this is 9. Okay, so notice that the greatest common divisor of 12 and 15 is 3. So 3 divides this and 3 divides this no matter what x and y are. Right, so 3 is going to divide this quantity no matter what. So if we have an equality like this and we want to know that there's a solution, it must be the case that this number is a multiple of this number here, which is the GCD of these two. But that doesn't guarantee us that there's going to be a solution at face value, right? It's just a necessary condition in order for a solution to exist, right? So we're going to need to investigate a little bit more why that necessary condition might be enough. If this is a multiple of the GCD, then we do get a solution for sure. That's what we're going to play with today, starting with what's called Bezout's lemma, which actually says that if you have two numbers a and b, and you have the GCD of them, which in this case is 3, then there actually is an integer combination of the two that equals the GCD. And to see why, I want to run through an example of the Euclidean algorithm that we saw last time with the actual example we saw last time and how to build an integer combination that equals the GCD from that. So the content of Bezout's lemma is that if C is the greatest common divisor of two integers A and B, then you can write C, that greatest common divisor, as an integer combination of A and B, meaning that there are integers x and y so that ax plus by is C. Now, we're not going to give a concrete proof of this, but the way to actually do this is going to be illuminated by looking at a previous example of something that we did using the Euclidean algorithm. So here, what I've done is ran through the process of finding the GCD of 2923 and 1369 using the Euclidean algorithm from last time. So these are the steps, and according to our algorithm, this first non-zero remainder actually is the greatest common divisor of the two numbers. So this is the thing, according to Bezout's lemma, that we're trying to write as an integer combination of 2923 and 1369. And the way to do it is to actually think about running this Euclidean algorithm sort of in reverse. We'll start with the 37, and I'll write it here. And recognize that we can write 37 as an integer combination of 185 and 74. It's 185, maybe I'll write it in the same format, times 1 plus 74 times negative 2. By moving the 2 times 74 over to the other side, we get this integer combination of 185 and 74. Okay, now we've sort of used this equation of the Euclidean algorithm. We can now do a similar substitution using this equation right over here, where we can write 74 as an integer combination of 1369 and 185. Right, so as a consequence, if we replace the 74 with this combination of 1369 and 185, we'll have this in terms of 1369 and 185, which will make this whole thing in terms of 1369 and 185. So if we do that, we have this 185 times 1, which stays, and then we replace 74 by this combination here, 1369 minus 7 times 185, and then multiply by negative 2. And so now if we expand and collect the terms, we'll have 1369 times the negative 2, plus 185 times a bunch of copies of 185. We have 1, and then we have this 14 of them here, so it's 15 of those. Okay, so now we've done this replacement and wrote 37 as an integer combination of these two, so you can imagine we're going to do this again with this 185, replace it as an integer combination of 2923 and 1369. Okay, if we do that, we'll have the 1369 times negative 2 still, plus this replacement for 185, 2923 minus 2 times 1369, and multiplied by this 15 factor. Okay, so if you collect terms here, we get 1369 times negative 2, and then a negative 30, so negative 32, plus 2923 times 15. So here is a pair of integers x and y, for which 1369 times x plus 2923y is 37. Great, so you can imagine how one would write a general proof of this. It might be kind of messy, but the idea is to say that at any iteration you keep substituting back the previous remainders into this process, and then eventually you'll get down to the original two numbers you were trying to find a greatest common divisor of. Cool, so Euclidean algorithm actually gives us this interesting consequence that you can write the GCD of two numbers as an integer combination of them. So let's actually see a number theoretic consequence of this in terms of divisibility that completely evades using any type of mentioning of prime factors. Okay, so here's a type of number theoretic property that you can prove. It's proposition 6 in the book that we're following. And it says if m and a and b are integers, and you have this phenomenon that the GCD of a and m is 1, then if this is the case that m divides ab, then m is forced to divide b. So before actually giving an argument as to why this is the case, let's actually talk about what the meaning of this statement is. So what you're saying here is essentially a and m don't have common factors here. So if m is dividing this product, then m shouldn't really have any factors in common with a because of this, so m should completely just divide b. This will become really useful in the situation that we're dealing with prime numbers eventually, where if you have a prime that doesn't divide a, then their GCD is 1, and so you get a consequence like this. Okay, so how do we actually go about arguing this without using prime factorization whatsoever? We can actually use this lemma right over here, right? And think about the fact that because the GCD of a and m is 1, we can find integers x and y such that ax plus by is 1, or ax times my is 1. Okay. All right, so we're given here that m is something that divides the quantity ab, and our hope is to prove that m divides b somehow. It doesn't seem clear that we can get that from here. But what we can do is introduce something into this expression to be able to establish that m divides b. And an idea is to introduce a factor of ab somehow. Now, one natural way to do that is to multiply this by b. But if you want to multiply this by b, it makes sense to multiply everything through by b. So we can say this implies, and maybe I'll write this in black so that it's clearer. This implies abx plus mby is b, multiplying everything here by b. Okay, so the information we're given here is that m divides this quantity. So if m divides this quantity, then m divides this. All right, but m automatically divides this because we have a factor of m right over here. So this expression here is a multiple of m plus a multiple of m. And so this right-hand side must be a multiple of m as well. So this implies that m has to divide that right-hand side, which is b itself. I remember when I first learned this, I thought it was really cool because I had seen arguments like this using prime factorization, and the actual arguments get messy because you have to write a general expression for how a factors into primes, b factors into primes, etc. It was nice to see this format. Now, it might be the case that you don't even have any idea about a proof of this using prime factorization. We haven't talked about primes whatsoever, and that's perfectly fine. It's neat to be able to establish things that feel intuitive using this Bezout's lemma. Okay, to end off this section then, what I want to do is talk about how we can look at Bezout's lemma and make a strengthening that actually gives us a complete characterization of the greatest common divisor of two numbers in terms of integer combinations. And that's going to set us up very, very well for solving linear equations in two variables where we restrict our variables to integers in the videos to come. Okay, so here's a characterization of the GCD in terms of integer combinations. And it says the following: if you have three numbers, C, A, and B, I'll just assume they're all positive, then C is the greatest common divisor of A and B if and only if the following properties hold. C divides A, C divides B, and C is an integer combination of A and B. So these three together imply that C is the GCD of A and B, and C being the GCD of A and B implies all three of these. Okay, so this is actually really quite interesting. We're going to see some consequences of this a little bit later. I want to just go over the idea of what an if and only if is. So this statement is saying then this happens if this happens. So we're saying if all this is satisfied, this happens. And the only possible way this happens is if this happens. That's the only if part. So in order to prove something like this, we need to establish, if we call this expression 1 and these three expressions combine 2, we need to establish that 1 implies statement 2 and 2 implies statement 1. Okay, so I want to start with, again, just because of space on this board, I'll have mostly sketches of proofs here, but they outline the details mostly. So first of all, let's show 1 implies 2. Okay, so if C is the GCD of A and B, then you get all three of these. So first of all, C divides A and C divides B because, well, why? Well, C is the greatest common divisor of A and B, so it definitely is a common divisor, right? So it does divide both because C is a common divisor. Because it's the GCD. This doesn't seem like we're actually proving something. It seems like we're restating exactly what this means. But this is part of being a greatest common divisor, so it's a little awkward, I understand. Okay, then finally we need to know that C is an integer combination of A and B. This came from Bezout's lemma. So I'll use this symbol for there exists. This is a universal math symbol used for existence. So there exist x and y in the integers. This is element of integers such that ax plus by equals c by Bezout's lemma. So in some sense, we've already had result 2, all three of these things, from the fact that 1 is true by things that we've built up already. Okay, so let's go ahead and prove that if 2 is true, then 1 is true. Okay, statement 2 says that C is a common divisor of A and B, and then you also have this extra stipulation, and for some reason this extra stipulation, what we need to argue, forces C to actually be the greatest common divisor. So why not take a different divisor and show no matter what that divisor is, it has to be less than or equal to C. That would establish that C is the greatest common divisor because it's already a common divisor of both A and B. So we'll let D divide A and D divide B, meaning that D is a common divisor of both. And then let's see why D would have to be something that's less than or equal to C itself. Okay, so well, let's look at this expression. D divides A and D divides B. So D actually has to divide this AX part because D divides A. So D divides AX. Similarly, because D divides D divides BY. And this implies D divides the entire quantity AX plus BY. We could have skipped the step of going to here and then here because we proved in the last video that if D divides A and D divides B, then D has to divide any integer combination of A and B, and this is an example of one. Okay, but it was nice to go over that argument anyway. So D divides this integer combination, and this thing actually is C, so this is saying that D divides C itself. Well, if D divides C, then D actually has to be less than or equal to C. D can't be something greater than C. So we picked an arbitrary common divisor of A and B and showed through this argument that D has to be a divisor of C. And that means that D is forced to be less than or equal to C. Since D was arbitrary, that means that C actually is, among all the common divisors, the greatest one. Okay, cool. So let's actually see an example of using this to try to establish GCD properties of some kind. Okay, let's look at an example of actually using this. So say we had that D was the greatest common divisor of two numbers A and B. What would you expect the greatest common divisor of A over D and B over D to be? Well, it seems like in this case, we're pulling out all the possible factors of d from both of these. So really, it feels like these two shouldn't have any common factors at all because the greatest common factor between them is d, and you're pulling out all the d that you can out of these. So you'd think that this thing is 1. Okay, now, if you have some background with prime factorization, there's a way to prove this with prime factorization. Writing it out is kind of a little bit tedious. But now we can appeal to this other characterization of the GCD to do this in a different way. Here's our candidate for the GCD of these two numbers right over here. So this is like our C. So we're trying to prove that C is the GCD of these two, so we need to prove that C divides each of them, and C is an integer combination of them. Okay, so first of all, C does divide A over D and B over D because D divides A and B, so A over D and B over D are actually integers, so 1 divides both of those. So we can sort of have both of those in check. Now the question is why 1 is an integer combination of the two. Well, we're given that D is the GCD of A and B, so that means by Bezout's lemma, we can find integers x and y so that ax plus by is d. Okay, so now that we have that, if we want to find an integer combination of a over d and b over d that's 1, which is what we have left to establish, we can actually use that to get that here. And we can do that by dividing all of this by d. If we do that, we get a over dx plus b over dy is 1. Right? So 1 actually is an integer combination of these two. And that's the last thing we need to establish. That tells us then that the greatest common divisor of a over d and b over d actually is 1. All right, so let's look at one last problem in this using Bezout's lemma. That's a bonus problem for this video. So the problem we're going to solve using Bezout's lemma is Putnam 2000 number B2. And it says if you have n greater than or equal to m greater than or equal to 1, then this expression right over here, the GCD of mn divided by n times n choose m is actually an integer. Now what this quantity here is this n factorial divided by m factorial times n minus m factorial. Okay, and so the thing is, if you were to use prime factorization, this thing on the top is going to look messy in terms of m and n. But if you instead use Bezout's lemma, some things fall out, right? So Bezout's lemma says we can find an integer x and an integer y so that this quantity in the numerator is mx plus ny. Right, and now we're dividing by n, and we're multiplying by this quantity n choose m. So you notice that if we rewrite this, we can rewrite this quantity as m over nx plus y times the quantity n choose m. And if we're interested in this being an integer, we only need to care about this piece right over here because y is already an integer itself. So really what we're investigating is why the quantity m over n times n choose m times x is an integer. And we can play around with this quantity to figure out that this happens to be an integer. So let's erase some things here and actually work that out. So this quantity here is m over n times n factorial over m factorial times n minus m factorial. So we divide out the m to get an m minus 1 factorial here, and divide the n to get n minus 1 factorial here. And that actually gives us the same thing. Notice here we have this minus this as a contribution here, and this minus this is this quantity right over here. So this is n minus 1, choose m minus 1. And since we stipulated that n is greater than or equal to m is greater than or equal to 1, this thing is actually an integer. It counts something. We'll learn that a little bit later in the course. Cool. So a nice sort of short way to solve a problem on a relatively challenging math exam using this Bezout's lemma. So I hope you liked today's video. If you did, definitely click the like button. And if you want to see more videos like this and see more of this actual video series, subscribe to the channel.